Okay. Where is everyone? Damien, can you see the board? Can you read the question? Okay, could you try this? Say marker, but give you about 5 minutes to try this question or think about this question. You can write on your separate notes. Just hello. Come in. 잘 지냈어? 왜?
생활 패턴이 너무 망했어.
밤에 늦게 자니? 밤에 늦게 자?
6시에 잤어요.
이제 바꿔야지. 자, 시작해보자.
저것까지요?
그런 거 같은데?
좋네요.
아니, 유튜브로 지금 듣고 있어, 지금.
라이브에 아니면 그냥 올리시는 거예요?
라이브인데? 너 지금 나오고 있어.
그래요?
thank you. 자, 29.8. Give you about 5 minutes. Try to. Do you have a year 11 chemistry? It needs to be marked, yeah?
I don't know what the answers are for this.
Okay. These one here. Yep, I will send you the answers.
I think the other ones in there, but there's like a huge stack.
Yeah, this is something that they needed to do. I'll leave that for now. Okay. Can you also write it down, total marks and percentage? Yeah, cheers, thank you. On that, Peter, could you turn the airdrops on? Yep, just for everyone. Yeah, change that to everyone so I can send you that. Three more minutes. Okay, let's start about this question 29. This is a marker question in school exam previously. Yes, you start to get some higher marks, like from 6, 5, 6, 7, up to 8. To answer this question, you actually need to know the difference between metallic, ionic, and covalent bondings. And to understand the bonding, you actually need to understand about what is going on inside of the valence electron. So what I mean by the valence electron is the outermost shell electron. The electron is located at the outermost shell. So we learned about this some trends in the periodic table, that on your left-hand side of the periodic table, we have the elements that have less than valence electrons and less than 4. So let's think about what I mean by having less than 4 valence electrons. So according to, you can copy that down on the back page of your the question, so you can just make it as a separate note. According to the octet rule, remember what I mean with the octet rule means they want to get the full shell. They want to make the full shell every single time. So when the valence electrons are less than 4, for example, 3, 2, and 1, they tends to, they have a tendency to lose electron. Because for them, for elements having 3 to 1 valence electron, for them, it's much efficient to lose electron to make a full shell rather than gaining many electrons. This gives a very special characteristic that we call this the metals in the periodic tables. Okay, so metals and metal have a tendency to lose electron, and means that higher metal reactivity is defined as tendency, higher tendency, the greater tendency of losing electron. Okay, now on the other side, we have another some of the elements that once having more than 4 valence electron, they're having a tendency of gaining electrons too, because for those having like a 5, 6, 7, and 8, up to 7, don't worry about the 8, 7. It's for them, it's much better to gain electrons rather than lose one. So these are known as the non-metals generally. And because of this, high non-metal reactivity is defined as greater tendency of gaining electron as opposed to high non-metal reactivity. So we learned about the different types of the terminology to describe the tendency. So, for example, electronegativity. Okay, Karen, what do you mean by the electronegativity? How do you define the electronegativity? Please revise that. Electronegativity means that tendency of gaining tendency of losing electrons. So high electronegativity means that they have simply love to lose electron more and more. So in other words, metals, as they want to lose electrons, gaining tendency, so been a while. So electronegativity of the metals are lower electronegativity, but for the non-metals, electronegativity is greater. I hope you remember the trends in the periodic table from the left-hand side to right-hand side. As going across the period, the electronegativity gets increased due to that increased number of the valence electron. The reason is the greater electrostatic force towards the nucleus. Again, you will get these type of questions a lot in the school exam, so make sure you prepare that. We also have something known as first, or sometimes simply known as first ionization energy, the energy required to lose electron. As it's getting harder it's getting easier to lose electron for those elements having less electrons, valence electrons. The first ionizing energy will share the same trends as the electronegativity, which means it will have a lower electronegativity in the metals. For the non-metals, it'll be opposite. First ionizing energy would be great due to that reason too. Okay, so we talked about a lot of the electronegativity, first ionized energy. I mean, you had a massive homework related to those, your holiday homework, that you need to study for those in terms of the periodicity. So why do we need to know about those trends or like some properties of the metals and non-metals? This describes you what happens to the bondings between each of those. So when we talk about metal, or metallic bondings. This means this is only be the combination between metals and metals. That if you only have the metals available means that they all have a tendency, they have a characteristic of losing electron. They do not like to gain electron at all. So I describe that as they are tossing the electrons to each other, like playing volleyballs. So it gives the very special characteristics. One is they are tossing the electrons to each other. Therefore, it creates very specific physical and chemical properties. First property is there will be lots of the free delocalized electrons available and the metal ions forming the something known as lattice structure. I described the lattice structure as this is called a metallic lattice structure then. Exception would have been the mercury, that it doesn't have much interactions, so they can have the liquid state. So this gives us some characteristics in the room temperature that metals therefore having a good electric conductivity. You'll have the solid at the 25 degrees Celsius, the room temperature, except the mercury Hg. Okay, it conducts. It also be a good thermal conductor, electric conductivity. I talked about it. High melting and the boiling point. They have a really high melting and boiling point. You think about how to boil, melt the metals. It requires quite a lot of those energies. Okay, that's basically what happened between metals and metals. Remember that it shares the same characteristic we have talked about in metals field. Now, when we have metals between the combination between metals and non-metals, it is slightly different too. It means we get this different trends. This is called the ionic bonding. So unlike the metallic bonding, ionic bonding would have the characteristic of the formed by the transfer of the electrons from metals to non-metals. The why is that? Why you have to realize why it must need to be from metals to non-metals, why the electron must be transferred from the metals and non-metals, not from non-metals to metals, because of that characteristics here again too. That metal have high tendency of losing electron, non-metal have a high tendency of gaining electron. So it'll be a perfect combination that one is love to lose, one is love to gain electron. So what do they do? Metal becomes two. Metals become the positively charged. Cation. Non-metals become the negatively charged. Anion. So we haven't gone through many examples too. So for example, sodium and chloride will now be bonded due to that positivity and negativity. So due to that positive and negative, there will be a strong ionic bonding due to the positive and the negatives of the ions. You can simply think like as this is kind of working similar to like putting the north pole to magnets to the south pole. They're just kind of attached together because they have opposite directions. So characteristics, they don't have the free electrons like the metals. So they have a poor electroconductivity. The reason is very simple, because they simply do not have anything free to move around. Everything is bounded. That comes in the solid state in the lattice structure too. Like a salt, table salt, or rock salt that comes in the solid state, but they can be, some of them are dissolved in the water. Now, you have to differentiate that to the molten salt versus the dissolved salt. That molten salt means that simply heating up liquid salt or the ionic compound without the water. So which means we put a lot of heat on the rock salt, kind of melt it. So we get the really kind of molten salt. It doesn't really need a water because we put a lot of heat to kind of dissolve, not dissolving, not melting it. Whereas dissolving salt means we have some dissolve in the solvent, like a water. So it doesn't really require much heat. We simply putting some pinch of salt into the water. That's what I mean by the dissolved salt. So unlike the solid state, molten and dissolved salt, they will have fairly good electric conductivity. Why is that? Because they're now free. The ions are now free to move around due to their free kind of dissolved by breakage of the bondings, or due to the dissolved formations too. So you can think about salt water. They're good to conduct electricity, but the rock salt itself is not really good at conducting electricity at all too. So that is the main difference between ionic to the metallic. Now compare that to the covalent. I need to use this space. Covalent is something that formation combination between two non-metals plus another non-metals. If you understood that, the non-metals and non-metals have a tendency of losing electrons only, so they do not really like to gain the electrons. So what they do, they are sharing the electrons. Between non-metals and non-metals. Something that's very important, they're sharing. It depends on how many vacancies they have. For example, fluorine has seven, so it has 1 in 1 vacancies. The vacancies will decide how many bondings they can form. For example, fluorine, which only has 1 vacancy, can form the single bonds only. Oxygen that has 6 valence electron, therefore 8 minus 6, having 2 vacancies, can forming up to 2 valence, 2 covalent bondings. Okay, and this is given the reason why the carbon is very special. Carbon has 4 valence electrons, which means it has 4 vacancies, so that they can forming up to 4 theoretically, but they can have a multiple the covalent bondings together. And we learned about how these are formed to each other. So Unlike the metallic and ionic, covalent structures are shared because they're forming, that comes out in the molecular structures more likely. I hope you realize, remember the difference between lattice and molecular. Molecular means that one or two are joined, whereas lattice means a network. We have a multiple of them, a network in the lattice structures too. And this will decide the physical state in the room temperature, because once we're having the lattice structures like this, we have a network, and that's what they're kind of connected together. More likely they comes in the solid state. And this gives the reason why metallic comes in lattice structures, comes in the solid state. Ionic also comes in solid state as well too. But for the this molecular structures, they are generally comes in the state of the gas or the liquid, but mainly comes in the gaseous state. And this is the reason why they comes in the diatomic forms too. Di stands for two. For example, this is the reason we get the O2, H2 in the elements, or Cl2, F2, whatsoever. Okay, and N2. And their state would be just simply gases, as we discussed before. So that is the one main difference between the covalent to the other structures too. The exception in the covalent we have is when we have the valence electron is equals to 4. Okay, again, according to the octet rule, 4 is kind of mid number between the 4 and the 8. So they can either gain 4 electrons or they can either lose 4 electrons too. So then what they do, they can share up to 4 valence electrons. So for example, is carbon can form 4 valence, 4 covalent bondings. So we can have a network of the carbons like this. Okay, and as you can see from that, this is giving you that covalent lattice structure then it is easy to think about what would be the main difference in here. We have a covalent lattice structure, depending on. So we have a lattice structure. What would be then states in the room temperature? Would it comes in the gases, liquid, or solid? If we have a lattice structure. It would be solid, because the rest of those lattice we had before, they always comes in solid state. What is this? What is the carbon's network? This is called the graphite. Or this is called the diamonds. Okay, so they are not coming in the gaseous state. We don't have the gaseous diamond. We don't have a gaseous graphite. We don't have liquid graphite. They are solid state, and depends on structures. They can conduct electricity. They can also have different features too. Now, last thing you have to remember is, because we finished with that before you go to holiday, for those having the same element, so made of the same element but different structure, is known as allotropes. Yes, we discussed the allotropes. For example, graphite and diamonds, they are both made with the carbons, same elements, carbons only. But they are completely carrying a different physical properties. The diamonds are more shiny, expensive, reflective. Graphites are more black and used in different purposes too, more weaker. And because of the kind of type of bonding, so the structures they're forming are different too. This will come out in your topic test next week. Not next week, sorry. Like sometimes later, not next week. Okay, I won't go harsh. Okay, you will get the module test once we finish the module 1. We'll probably finish module 1 in 2 weeks. So after that, module 1 test again and again and again. All right, so going back to the question they're asking you, compare the metallic ionic covalent bonding structure you actually need to talk about everything. Saying that what forms the metallic bonding? Why is the metallic bonding formed? Started from the metallic bonding formed due to the metals and metals combination because they have a tendency of losing electron. They have a rather tossing electron. This gives very special features of the 3D localized electron with the lattice structure with the ions. Therefore, carrying that very good electric conductivity as well as in the solid state in the room temperature too. Guys, you don't have to. I mean, the parts that you need to understand is simply the valence electron parts. You just need to understand, oh, okay, the valence, the number of the valence electrons are 3, they lose electron. Up to there is where you need to understand. From that, after that, this is something that you must memorize. Okay, no excuse. You gotta get the very similar type of question again and again too. Ionic, the combination between metals and non-metals because of the chemical property differences that metal loves to lose, non-metal loves to gain. There will be transfer of the electron from the metals and non-metals. Therefore, they're forming some cations and anions, forming the lattice structures called that ionic compound, the salt. That ionic compound will have the solid state in the lattice. Okay, it will have a poor electroconductivity. And they can dissolve in the water. Depends, but they can. Now, depends on what we have, the molten salt or dissolved salt. Okay, molten as in like we put a lot of heat, we heat it up, so kind of melting all that salt into the liquid salt. They will have some good electric conductivity because it simply means that salt ions are free to move around. Dissolve salt, put it into the water. You can just simply thinking about salt water. That also can conduct the electricity because they're no longer be in the lattice structure. Lastly, covalent bonding. There are a few of the covalents. We have a combination between non-metals and non-metals. They are basically sharing the electrons and forming the bonding. They're really strong bonds to each other. Okay, so molecular structure-wise, they are coming the molecular structures. Therefore, their physical state would be more likely gas or the liquid. More likely gas, the element forms. They exist in forms of the diatomic that comes in the 2 in each here. Okay, and therefore, you can talk about the boiling point, the melting point. They have really low boiling point because they comes in a gaseous state in the room temperature. Okay, do they conduct electricity? I don't think so because they can't. We can't conduct electricity in the gas over here. Now, when the valence electron number is valence electrons on number 4, for example, carbons, they can share up to 4 valence electrons. Means that they can form lots of the bonding between the same elements. For example, carbon can form this kind of network. We call that as covalent lattice structure there. This is the case we get this solid state. Therefore, they can have a various type of the allotropes made of the same element with the different structures. Good example is graphite and diamonds. We also discussed about sulfur that having different structures too. So it makes sure you understand and study for the bonding. This is where we're up to before the holiday. Okay, so that simple one question is actually asking you everything you learned from module chapter 1 to chapter 6, I assume, in module 1. Okay, any questions? Jenny and Damien, I'm watching the comments too, so if you have any questions, please comment it. So leave your comments there. And thanks for joining the live class. Okay, let's move back to the where we're up to. So we were up to there before, and I'll ask you to do some questions. We actually didn't do the questions related to that, so let's try some questions related to these. Page 192, please. Okay, let's do some namings. It's been a while, so could you answer question 5 and 6 now, please? That is the page 192 on your workbook. Yep. Hmm.
One conduct electricity.
Why?
Graphite is good conductor.
Is it a good conductor? I mean, it does, but does it? Can we consider that graphite is a good conductor?
But it said do not.
It does not. Yeah, it does not much. What about diamonds? Why not? That's what the question is asking.
No free.
Why there isn't any free electrons then?
That's crazy.
Did you name them?
Yes.
Okay. You give me an answer for the question A, see how it goes. So what we have to consider here is you need to understand and remember them, the rules of the naming covalent compounds, that we are putting some least electronegative first. So compare the carbon and chloride, which is more less electronegative. Carbon and chlorine, which is less electronegative. If you're not too sure, I can give you the periodic table there. Which one is more or less electronegative? Carbon is less electronegative, so we write the carbon first. How many bonds, covalent bonds, carbon can form? How many covalent bonds? How many valence covalent bonds? 4. What about chlorine? How many can it form? Remember that chlorine has 7 valence electrons? How many vacancy? It has 1. So how many bondings can it form? Chlorine? 4 carbon. It can form up to 4 covalent bondings. For chlorine, it can form up to 1 covalent bondings, which means carbon can form up to 4, whereas only have 4. So we need to have 4 of those to make a batch. So it will look like this. The name of this? Carbon. 4. 4 stands for tetrachloride. Check your answer whether you did it right or wrong. For the rest of the B, C, D, E, and E. Okay, same for the nitrogen and the bromine. Bromine. Nitrogen can form up to 3 covalent bondings. Okay, I'm not going to explain the why it can. It's just simply known as a pre-knowledge from now. You need to study it. You need to study like the valencies and memorize the valencies as well too. 3 covalent bondings. Bromine can form up to 1 covalent bonding. So when they are formed, it becomes NBr3. The reason why I put the N first is because nitrogen known to be a less electronegative than bromine. This is known as nitrogen tribromide. Next one, we have silicon and oxygen. Silicon is less electronegative than oxygen too because it's located on the left-hand side of the periodic table. Therefore, silicon can form up to 4 covalent bonding, whereas oxygen can form up to only 2. So it becomes to silicon. This is known as silicon dioxide. Next one, H and F is simply hydrogen can form up to 1 covalent bonding. Fluoride can form the 1 as well too, known as hydrogen monofluoride. Sometimes known as monohydrogen monofluoride too, but we tend to skip the number 1, the mono, in the front of the first element or non-metal element. E, P, and F. Yeah, second chance. P, phosphorus. How many covalent bonding can phosphorus form? 3. What about fluorine? 1. Therefore, unit B, P, F, 3. Naming? Phosphorus. Very good. Trifluoride is how you name these non-metal combinations. Okay. This is something that different to the ionic compounds too. I hope you memorize all that covalent ionic compounds. For example, CO3 2 minus. What's that? Stay back. Take your test today. I told you, like I'll push you, I'll make you to memorize that 100% because you have no chance to survive in chemistry without knowing that. Question 6. Explain why covalent compounds do not conduct electricity in either the solid or the liquid state. Okay, something that's very, very, very important here. Covalent compounds are formed by sharing the valence electrons. This means there is no free electrons nor that ions available in the we call it covalent structures. And remember that electric conductivity is all about, you can just think that electric as electric conductivity is equivalent to the movement of the free ions, free electrons, or the ions. There will be no or pole electric conductivity in those covalent networks or the molecules. No or pole. Okay, so it simply means there's nothing free. There's nothing free to move around, even though we put into the really high voltage so that nothing is able to be moved. It's kind of indicated by poor electric conductivity too. Exception, yes, graphite. Let's talk about the graphite and some differences too. It's actually, we kind of discussed it before. That's on your page. I kind of use the page, what's the page number I'm missing? Page 189 on your carbons too. I briefly described about like what difference between graphite and diamonds. So graphite is more like a layered, okay, which means I would like to have a look at the edge of the layers. This carbon here forming two bonding only means this carbon as well too. So they have some free electrons available. Okay, so at the edge, at the edges, some free electrons are available. This gives them to have a small amount of the electric conductivity. What about rest in here inside? They're not able to conduct the electricity too. And we also discuss about why the graphite looks black. Why is it black? Having a black color in means that they are capturing the light. So when the light comes in along to the layers, lights get captured inside of the layers. So there will be no escape of the light at all too. They are absorbing all the light in between the layers of the carbons. For the diamonds, however, the light comes in, it gets reflected inside and comes out. So that this is why they're shiny, they're reflective. Okay, they don't have any edges. They don't have any like electrons edges. So it means, which means that they will have a poor electric conductivity. Okay, also they're not layered. They're more structured, like in a more like condensed structure too. Okay, it's good to know the main difference between the graphite and diamonds in terms of their physical properties to the related to chemical structures. Any questions? Okay, this is where we're up to, where you should finish it up to last week. I mean, like in the holiday. Let's move on to the yeah, let's do that. Chapter 6, please. We're going to finish the chapter 6 today. So we're going to talk about something in terms of the structure, like a structure shape. Shapes of the covalent structures, or the molecular covalent or molecular covalent molecular structures, I should name that as. Okay, pre-Osham knowledge for to understand the shapes of the covalent molecular structures. One, covalent, again, means they're formed by the sharing of the electrons. Okay, it's all about sharing the electrons. Two, electrons are negatively charged. Particles, that means that when each electrons are repelling each others due to their same charge or negativity. This is kind of pre-Osham knowledge you need to understand about the shapes. Simply means when we have two electrons comes along together, they love to push to each other. They love to push. Okay, so I want you to think about a situation in here. I have a one electron and another electron goes like this. Okay, this simply means when I try to put them together in the closed place, because they are negatively charged, they will push like this. Okay, what if I have three? I try to put them all together here. Remember that they are saying identical to each other. So theoretically, when I try to put them together there, they will push each other into the different direction. Okay, what about I have a four? In terms of they are repelling each other, one goes up, one goes to this direction, one comes out of the page. So what they try to do is they try to balance it out. Like angles. So in this type here, the angle between that would be 180. Angle between here would be 120 degrees for each of those, because they are equally pushing to each other here. Third is it will be 109 degrees there, because it comes out. We call that kind of tetrahedral shape, or like making some 3D shape of that. I'll show you in the modeling in a second later. Okay. For to understand the Vesper theory, or like a valence shell electron pair repulsion, this is actually basics you need to understand. That electrons, when anything comes into forming a bonding, they try to push each other due to their negatively charged. So, few things you need to memorize. On your few things, you need to memorize the basic shapes. Basic, or like you can talk about fundamental. Basic shapes. Now, if we only have a two, like a compound made of two elements, they are having a basic shape of the linear. That'll be forms like this. That's a linear. Okay, there's nothing more. If I have a three, I give it that. Okay, if I have a three, it comes in the trigonal. Trigonal spelling. It's in a triangle. It's a tri means three. Trigonal. The planar. So it shows on your page 210. It shows the trigonal planar shape. That gives you that is form the three. The each goes like this, or it comes like this as well too. So when we have two things attached, it comes the fundamental shape, the linear. If we have the three elements attached to one essential one, it'll be three trigonal planar shape. if a 4 elements attached, okay, the fundamental shape would be known as the tetrahedral shape. That comes like this. One is going up and down, and one comes to forward or backwards. I probably have the modeling. I'll show you in a minute. Okay, so a tetrahedral shape, page 11 shows a tetrahedral shape. It shows like this. It seems like we have a kind of pyramidals and comes the up. Okay, these in year 11 levels, these are the only 3 things that you need to memorize. And one more thing, you need to take that as a lone pair is considered as an element. So what do you mean by the lone pair? Lone means they're long pairs. Okay, there are the pairs of the electron that involve in the chemical reaction, the chemical bonding. So I show you the example. We have an oxygen and oxygen. Show you the oxygen in blue, oxygen in purple, like this. Oxygen, blue oxygen has 6 valence electrons like that. Purple oxygen also has 6 valence electrons like this. Okay, as you can see, out of 8, it has a 6, so it has a 2 vacancies. It can forming up to 2 covalent bondings. So what do? They're forming a bonding called covalent bonding or double bonding. So it looks like this. The oxygen, blue, purple will form the bonding between them. Goes like that. In terms of the Lewis dot structure. And the rest of those pairs will be lining up. Comes the pairs of those like this. Okay, I'm calling this the lone pairs. Pairs as in like a pairs of the electron. They're lonely pairs. They did not get involved in the forming of the covalent bondings. They're left as a lonely. So this is why I call that lone pair. Okay, so only 4 electrons are involved in the forming the covalent bondings. Others are shown the lone pairs like that. Does it make sense? Okay, now why is it so important to understand lone pairs? I give you some Vesper theory rules. This is probably the simplest way to understand. I give you some examples. I have, say, carbon, CO, and 2. Okay, now how do I draw the CO2 in forms of the Lewis structure? Is carbon in the middle are forming a bonding with the 2 oxygens like this. Okay, then you will also have the electron lone pairs on the top. Goes like here. Now what we have to see is we need to see the central one. This is called central atom. The central atom does not have any of the lone pair. So what would they have is we only say the central atom only has 2 elements attached. I don't care about what lone pairs they have. I only see the central atoms, they having 2 attached. Okay, if there's nothing happen, I just see that follow the fundamental structure of the 2 element, which is what? The linear. So the carbon dioxide must have the linear structure. Does it make sense? Okay. What about this one, H2O? H2O. Okay, what would be the central atom in the H2O? Central atom. Oxygen. So we have an oxygen in the middle. Okay, tell me more. Hydrogen will be attached. Forms like this. Okay, how many bondings can hydrogen form? 1. How many bondings can oxygen form? 2. So they will form the bondings like this. Okay, now consider the oxygen there. Oxygen has how many lone pairs then? You will have 2 lone pairs. It's a 4 in total. In pairs, you have a 2 lone pairs. So now, this is something that's very important. The central atom, which is the oxygen, can you see that? Now it has 2 elements plus 2 lone pairs. Does it make sense? Now, how many in total? We have a 2 and 2. So in giving you the total of 4. So what is the basic shape of the 4? It's called a tetrahedral shape. Okay? Now, tetrahedral shape is look like this. Now, what you have to consider here is lone pair is considered as an element, but it doesn't really working as an element. So what you do, I ignore these 2. What do you get? You get the bent shape then. Why? For the 2 lone pairs, it will actually form like this. We will have oxygen and hydrogen to the lone pairs on the top. This is how we get the bent shape. Does this kind of make sense?
So if the central lone pair,
Mm-hmm.
it is in shape.
Sorry, say it again.
So CO2 and
Central atom,
doesn't have the lone pair.
it only has how many elements? No, it has 2. It's 2 attached. Oxygen, how many is attached? About 1, 2, 3, 4 in total. We take the lone pair as an element too. Does it make sense? Okay, I show you that, and I bring the modeling. It's actually better to use the modeling. Give me a sec. Lucky that you have personal one. Okay, this is modeling that I usually use to show that special theory. So what I'm going to do is I'm going to make the modeling of this. So I show you that what the tetrahedral shape look like. So black is generally the carbon form of tetrahedral shape. And each of those are representing the bonding. So like a little piece of plastics there. So what I do, I connect them to make a shape of the tetrahedral shape. And use this. We got one. Yeah, make a tetrahedral shape using this. This is what I mean by tetrahedral shape. So you can see that in the middle central atom there, okay? It's surrounded by the 4 in equal angles. Can you see this? This kind of pyramidal shape, a tower shape, and sometimes describe that as. So let's go back to like what I mean by the water. Water, the oxygen central atom has 1, 2, 3, 4 in total. So the fundamental shape would be tetrahedral from the 4. Now, what happened is because the 2 of those 4 attached are actually known as a lone pair, they do not really exist. So what we do, I replace the lone pair with a little small piece of plastic. Okay, so what I do, only 2 exist. I take 2 out, and attach the lone pairs on the top here like this. Then you will see from the tetrahedral shape, now we get the bent shape. Can you see that? Okay, these 2 are representing lone pairs. Yes, they are still attached, but not as working as a bondings. So it looked like this shape exactly. Does it make sense? This is how easy it is. Do not go too much details about it. I'm just explaining you how to find the shape exactly. This is the easiest way you can do. And this is the technique that we use in this chemistry Olympiad as well. Does it make sense? Okay, let's do more. What about NH3? So first thing, you need to start from what's in the central atoms too. We have us and the NH3, we have a central atom of the nitrogen. Okay, nitrogen can form up to 3 bondings. So it will form 1, 2, 3 with the hydrogens, and in lone pair, there'll be only one lone pair on the top. So let's start it again. We have a central atom, which is nitrogen. It's connected to 1, 2, 3, and 1 lone pair. So 4 in totals. The fundamental shape of the 4 is tetrahedral. Then, as the one of those are the lone pairs, what happens is this will form something look like this. I call this is known as the, as you can see, this is the making a kind of triangle. So I use the following term, trigonal. But unlike the planar shape, unlike the plane shape, this is making some kind of pyramid. So this is known as trigonal pyramidal shape. Okay, it's given on here. There's a pyramidal shape, trigonal pyramidal shape. It's due to that. But the way we can find that shape is always started from the central atom. Give me more. Can I delete that now? Linear and trigonal. Okay. If it needs help, okay, let me know. Let's do more. What about CCl4? What was that? The carbon tetrachloride. Okay. Let's draw a structure of this. This is why you need to master this during the structure, the Lewis structures. Where's my black pen? Yeah, okay. Carbon is in the central there, with the 4 chlorines attached. Now, how many? How many attached? There are 4 attached. To where? To the central atom. Okay. Now, what's the basic, the fundamental shape of 4? Tetrahedral. There we go. Now, do we have any lone pair? Any lone pairs? Do we have any like electrons? No lone pair. Huh? You don't remember that you're the only one here. Okay. But today, this is what I mean here. That's central atom here. It's connected to the 4 without any lone pair. What's the fundamental shape of the 4? Again, right here, 2 linear, 3 trigonal, planar, 4 is tetrahedral.
So like if you draw Lewis structure
Yeah.
next to the chlorine,
Yeah.
like 6.
Do I care about lone pairs of chlorine? I don't care. I only care about the central atom. Did I care about any of those? Did I care about that one? No. I only care about what's in the center. The central atom is the most important. So 4 with the no lone pairs, straight go to the shape would it be? Shape would it be? Tetrahedral. There we go. Do we need to think twice? No, this is that easy. Okay, shall we do some more practice on this? There are more. The shape, okay, that's many. Page 218, please. What about pH3? pH3. Give it a go for the next 2. Shape of the hydrogen sulfide and phosphine pH3, please. Yep, just try to use that.
Pyramid.
Do the finish the next two. It is very important to just start with the during the correct diagram, the Lewis dot structures or Lewis structures, so that you're able to figure out how many lone pairs attached. Okay, let's go for the pH3 phosphorus. Now, phosphorus in the same line of the nitrogen, it can form up to 3 covalent bonding. So it will be like this. Yep. How many like in lone pairs then? It will be having one lone pairs on the top. So we have 4 in totals, including the 1 lone pair. Okay, taking that as the lone pair means that this will give us that missing one on the top. This is called the trigonal pyramidal shape. Trigonal pyramidal shape is the correct name. Okay. What about next one? H2S. H2S. Start from drawing the diagram. So we have a sulfur probably in the middle. It can form the bonding with the hydrogens like this. Okay. Only one bond can be formed in the hydrogens. Now, considering the sulfur, which in the same line, same group with the oxygen, how many lone pairs in the sulfur then? There'll be 2. There'll be 1 and 2 like this. Good. It would be having 4 in totals, including the 2 lone pairs. Therefore, having what? Making the bent shape. Is that easy? Okay. This is the rule for the VESPA theory to figure out the structure of the sorry, I forgot to name that. The molecular compound structures. I think we have more given here. Page 230, please. On the page, the question 8. It's not the same question, but could you find that the shape of those A to I then, please? Make sure you draw the structures of everything you have to figure out how many is attached in the central atoms. Did you draw the shape? Did you draw them? Please draw in the Lewis dot structure, please. Okay, let's start from the NH3. We actually went through that. First of all, you need to identify which is your center, the central atom. The nitrogen this time is the central atom you have, but the hydrogens are attached. And for the Lewis dot structures, make sure you show all the bonding is a dot like this. Okay, and then show the top, the lone pairs on the top here like that. Lines is a Lewis, not a Lewis dot structures, the Lewis structure. You have to differentiate the Lewis structure to Lewis dot structures. You actually lose a mark. I'll ask you to draw the Lewis dot. If you show me the Lewis structures in the lines, you will lose a mark. And there'll only be one mark only, so it's quite a sad way to lose. So what we have in totals, we have, nitrogen would have only one pair on the top. So we have 1, 2, 3, 4 attached. The basic shape, fundamental shape with tetrahedral, missing one due to lone pair is known as trigonal. Pyramidal shape. Okay. Second, we have a CHCl3, which is the central atom. C. Carbon in the center. We have a hydrogen and 3 chlorines, and show the bondings like this. Okay, rest. Yes, you need to show every single missing bondings like that. And what we have is we have 4 attached in the central atoms without losing any due to lone pair. And the shape is known to be tetrahedral. Make sense? Okay, same things, carbon in the center. We have a hydrogens attached. And chlorines here, like this. Make sure you show that all that pairs, but that doesn't really affect the shape. This is also be tetrahedral shape. What about FeO? F2O, which goes in the center, is the oxygen that goes in the center. That formed the bonding with the fluorines like this. Okay, now it has 2 lone pairs on the top, which means in total number of the attachments, we have a 1, 2, 3, 4, but 2 of them lone pairs, so it shows the bent shape. Does it make sense? Okay. HBr would be hydrogen bonded with the bromine. It's hard to see like which is the central because there's only 2. It's just simply linear shape. H2S, we went through that. It forms this with 2 lone pairs, so show the bent shape. HF, same reason for the HBr, it would be hydrogen with the lone pairs. Guys, make sure you practice the Lewis dot structures again. This is the easiest question you can get, but sometimes you lose a mark. It's a big loss. It's a linear shape. And H2O is a bent, as we know. Oh. 4 attachments to the lone pairs, so it'll be a bent shape. Too easy about the Vesper theory? Yes, I can explain it more further, like a more complicated of a Vesper theory, but you won't get the question in the school exam. So why would I bother to? I mean, I would just focus more on the type of question you can get in the school exam because you won't get this again in your year 11 and 12 once you finish that. But simple rule is memorize that 3 basic fundamental shape. Okay, from that, consider the lone pair as your attachment, but that do not really shows in the structure, so they will decide the type of the structures as well too. For example, the difference between tetrahedral to trigonal pyramidal, it has 1 lone pair that appears to be invisible, therefore kind of pushing them, making the pyramidal shape. Any questions? Okay, the last thing I want to go through that is from the shape of those, it's actually making something that very interesting. And you know what? I will go through that after we have a break. Let's have a break after this, okay? We just have a break. All right, let's start again. Okay, 4.5, page 219, please. I'm going to explain you about what I mean by intra and intermolecular forces today. Okay, let's bring it up. Intra and inter. So let's go word by word here. So intra. Okay, the meaning of the intra is literally explained as something inside. Okay, whereas inter means that in between. So what I mean by the inside, it means when we have a something, like if you think about something, the difference between intranet to internet. I'm not too sure whether you use the intranet a lot these days. Okay, just checking. Okay, intranet is like only for the small communities inside of that school's intranet. Okay, company intranet. Internet, you can connect with anyone outside of your communities. You can connect with someone in the Korea, someone in China, someone in the US. Yes, that's what we call internet, internetwork. Okay, same things we use. We use literal meaning of the inter to describe that something known as the molecular forces. Okay, so meaning of the molecular. So I hope you remember, like, what I mean, like structure difference between atomic molecules and lattice. That molecular means that something is connected one or another. Okay, but when we use the molecules, we do not have molecules quite a lot in metallic. We do not have the metal molecules. Metals comes in the lattice structures more likely. Okay, molecular forms means that molecular means that it's more about the non-metals covalent, non-metal covalent structures. Mainly is related to that here, and some of the ionic molecules too. Okay, so when we say intra, so let's combine it here. Intramolecular forces means that the forces or the bonds between the molecules, not the between, sorry, bond forces, bonds inside of the molecules is how we need to interpret the intramolecular forces. And we actually went through the many of the intramolecular forces that there are many. For example, we can think about metallic could be part of the what's going inside. That's between metals plus metals. That would be intramolecular forces between metal and metals. It's inside. Inside of that, I'm talking about this one is your intramolecular forces or bondings. Okay, we can also have ionic. That's between metals plus non-metals. Lastly, we also have the covalent. That would be non-metals plus non-metals. So all of those are talking about what is inside. So remember that intra always be inside the molecules. So that's basically talking about bondings, different type of bondings we discussed before. Okay, so it gives you some properties on page 219 there. So let's go through that. The physical property of the ionic compounds note to be hard, solid, brittle, high melting point, poor electric conductivity when solid, good electrical conductivity when molten, good electric conductivity when dissolved in the water. So we got to discuss that in terms of the chemical structures again too. Hard and solid, okay? Because of that, the intramolecular force is pretty high. That forms the high intramolecular force forming because they have a really strong bonding to each other. They're forming the lattice structure. or ionic. Lattice structure would be the right word to describe. Why is it brittle? Why is it like that kind of destroyed? It means that external force can shatter the lattice structure. If you think about the sea salt, you can just use your fingers or use your palms or whatever. You can just make this fine powders to it. That's what I mean by brittle. High melting point means that they are bonded really strongly. So to let them go, to separate one from another, it requires lots of energy. So that's indicating that high intramolecular force holding each atoms strongly from the heat. Poor electroconductivity, as we discussed before, there's no free electrons nor the ions available. However, when it's a molten, when we get some dissolve, not the dissolve, when we get lots of heat, get a liquefied, liquid salt, that means some ions are free due to the heat. Therefore, they are able to move around. Lastly, good conductivity when dissolving that too. So dissolved form, we call the hydrated. Hydrated ions are free to move towards the opposite poles. So again, I'm revising that what we learned about the bonding stats, while each of the metallic ionic covalent have a very specific physical properties, which means you will get these questions a lot. Okay, I guarantee you'll get at least one question in your yearly exam as well too. So covalent bondings is something that we discussed as well too. Next page. Now let's have a look at the electronegativity chart. This chart shows you that what actual electronegativity numbers they can have. So as we discuss about the trends in electronegativity, you just see that fluorine has the highest electronegativity of 3.98, close to 4. Okay, I hope you remember the trends of the electronegativity. Across the period from left to right, electronegativity gets increased due to that greater, stronger electrostatic force towards the nucleus. Down the group, electronegativity gets decreased because of the greater size of the atomic radius, therefore easy to lose, hard to gain. So as you can see, fluorine has the greatest electronegativity, as you can see from that too. Francium has 0.7 here only. Now, what you see there is, you see the trends across the periods would have the greater electronegativity compared to the down the group. I'm comparing oxygen and chloride here. Oxygen has 3.44, chlorine has 3.16, which means that across the period has the greater electronegativity than down a group effect. So this is something that you also need to understand, that because of nitrogen, and same for here, nitrogen would have the high electronegativity then of the bromine given over here as well too. Okay, now why is it so important to understand about electronegativity? Again, electronegativity means that have a tendency of gaining electron. Let me rewrite that here. Electronegativity means the tendency of gaining electron. Now, when we have combination of the hydrogen to hydrogen, for example, because they are forming the covalent bonding by sharing the electron, this is what I mean by that. The hydrogen that used to carry one electron here, when it's forming another hydrogen, okay, they are forming a bonding by making a bridge. or single breach. So this is what they mean by share. That throughout the breach, two electrons are able to move across. And what we see that what inside of the hydrogen, I can redraw that. The hydrogen is actually made with the one proton. Yeah, if you see that you're on a periodic table, hydrogen is the only one that having one proton, no neutrons. So what that means is electrons from this side are used to hanging around. Remember that electrons are negatively charged, protons are positively charged. Electron used to be hanging around to neutralize it. So neutralize it, the positive. Okay, now when they're forming a bondings, this electron here is able to go other side of too. So this is actually electrons, these electrons are equally neutralizing the positives. Does it make sense? Okay, this is what I mean, like they're making the same orbit. I call this as simply a covalent bonding. But because they are equally sharing, equally neutralizing the positively charged, I also call there's no charge whatsoever. This is called a non-polar covalent bonding. And still, I'm still talking about intramolecular force. Does it make sense to you? Yep. So when they're having, so which means that we have a condition for that. When two elements having very similar electronegativity, similar power, they do not need to, like they are sharing the electrons equally. Does it make sense? Make sense? Okay. So this is something that's very important. They are equally neutralizing that. But what about we have hydrogen, which is having one electron here again too. So I gotta draw the hydrogen again in terms of protons. We have hydrogen with the electron used to hanging around like this. What if this is forming bonding with the oxygen? So let's compare the electronegativity of hydrogen and oxygen. Hydrogen has 2.2 electronegativity. Compare that to the oxygen, which is 3.4. So you see, oh, this is about like 1.5 times greater. This is actually greater amount of the huge amount of the difference between a huge amount of the electronegative difference between hydrogen to oxygen. So okay, which means when you're thinking about the meaning of the electronegativity, means the tendency of gaining electrons. Oxygen has higher power of gaining electrons too. This can be reinterpreted as this. This means that it has greater pulling of electrons towards. Means it's kind of pulling electrons towards itself much greater force. So that's what happened. When these two are decided to forming a bondings, now this electron that used to belong to hydrogen will now forming a bonding, yes, but what actually happened is this. Instead of them making the equal bondings like that, this electron here that used to come here, I use the green, actually green's better. The electron go here will be hanging around in these regions only. Now, you see the difference between that equal share to the unequal share. That means this electron will never, ever reach to other side. This not happening because the oxygen is so powerful, it is pulling the electrons towards itself to almost like dragging the electrons towards that. This means, yes, we're getting there. This means electron that used to belong to hydrogen will now almost belong to the oxygen. So for the oxygen side, it looks like they gain some electron, but not like a full gained. I call that as partial gaining of the electron. This is represented as partial as delta negative, because electron is negatively charged. Okay, in simple symbols, we describe that as partial as a delta negative here like this. Sometimes describe that as all delta negative like this. What about on the side of the hydrogen? Hydrogen almost lost electrons. So almost lost. It's not lost yet because it's still hanging around in here. But you will see that this side of the protons, which is positively charged, will never ever get the negatively charged. In other words, this side of the proton will never get neutralized. Does it make sense? Unlike this situation here, the electron is kind of neutralizing equally. This will never neutralize out the backside of the hydrogen. So I describe that as this is a partially positive. In a simple arrow forms, we show that means that we have going into this polarity, that plus is moving towards the negative here like that. This is known as the polar covalent bonding. And this is still part of the intermolecular forces yet. I'm still talking about what's happening inside, not the outside. Does it make sense to all?
What is it? H2O?
Yeah.
Is it still polar?
Good. H2O would be that oxygen still be powerful. So there will be what? Two positive and one negative in the top. Almost like oxygen is pulling those back towards to, like pulling towards to its side there here too. Okay. Now what you have to see there is I have 1 and 2 polarities. There are two polarities. Can you see that? One positive, one negative. There are two polarities. Instead of saying two polarities every single time, I describe that as this. Simply, because of that because of that polar covalent bondings, now they started to having something known as dipole. Well, the dipole stands for what? Di stands for two. Pole stands for polarities. Yes, you would have started to see that there are two polarities are formed due to that polar covalent bonding. What is generating polar covalent bonding again? That's due to that electronegativity difference between two. In other words, when we have a combination of non-metals that has a matching, that's not matching the electronegativity, more likely they form the polar covalent bondings, which is forms of the intra. Do not confuse this point, guys, yet. I'm still talking about what's happening inside. Polar covalent bonding is actually the intra, what's inside happening. Dipole is the what's happening inside. Does it make sense to all? Okay. It describes well the next page over here, page 2021. You show that polar bonding, non-polar bonding forms as this. Technically, when the unequal sharing happens when electronegativity difference is 1.7. But you will not ask you to memorize the electronegativity chart ever. But one thing that you have to understand is this. Let's bring up the chart for the reference. Okay, out of many non-metals, we only care about a few things. Hydrogen, okay, is something that's very important. Has a very similar electronegativity as a carbon. You see that 2.20 and 2.5 or 55 means that when carbon are forming a hydrogen covalent bonding, you start to say that this must be non-polar. Okay, does it make sense though? Now, when hydrogens forming bond with the strongest electronegative element, which is nitrogen, oxygen, fluorine. These three are known to be one of the three of the most electronegative elements. Hydrogen with the nitrogen, oxygen, and fluorine. Or the chlorine is too, but we can't ignore the different periods. Okay, in that, this is formed the strongest dipole generated. What do you mean by stronger dipole? Because due to what? Due to that, the greatest, the electronegativity differences. Now, yep. Well, any of the CHEM forms, yes, it will form that nonpolar. Means can have up to 4 CH bonds. All of those would be nonpolar in this case. Yeah, but it's negligible. The main point, the marginal point is 1.7. Carbon and hydrogen, we tend to say they have a very similar electronegativity. Okay, now, what about this one? When carbon is then forming a bonding with the halogen, X, that's the halogens. Okay, X as in like, this is X, group 17. Okay, X is a special symbol for the halogens. They're forming the polar bondings too. Or the, we call that as dipole as well. So instead of we having the hydrogen, if we have chlorines attached like this, carbon tetrachloride, okay, this would have some positive negativity, which means carbon inside would be partially positive, chloride outside would be partially negative like this. Does it make sense? It's all because of they have a massive electronegativity differences too, but not as much as the hydrogen to those over here. Okay, it'll be slightly polar compared to the hydrogens. Again, the standard for the electronegativity of being polar, non-polar is 1.7, 0 to 1.7 differences too. But you don't really need to like memorize the 1.7 as a standard there too. I'm just giving you some straight cuts that hydrogen with nitrogen, oxygen, fluorine has the greatest electronegativity differences. Therefore, forming the greatest, strongest dipole generated. Carbon with some of the halogens, we also can form the polar bondings as well too. Does it make sense? Okay, so something that's very important to understand, I'm still talking about what's going to inside, what's happening inside of the molecules. I'm still talking about carbon to hydrogen relationship. Make sense? What about this one here? I have a water, OH and a H. Okay, as we discussed that hydrogen is partially positive, the partially negative. And what do you call this? This is called a dipole. Okay, dipole is due to that intramolecular, or simply known as polar covalent bondings. You okay up to this point? Then, what if I have another water molecules comes here like this? I have a 1 and 2. Okay, just like this, the previous water molecules, this will also be partially positive, partially negative. Okay, that's a partially positive. Remember that is a partial means that they're actually not completely ionized. They're still in the process of gaining or losing electrons. So, but what you have to see there is the partial negative and partial positive. Because we have positive and negative, they will love to interact. They love to attract to each other. So there will be an interaction. Oh, I call the interaction. But instead of using the interaction, which is the kind of literal meaning, I'm using the fancy word called this is called intermolecular force. Again, inter means in between. So in between the molecules, now there are what? There are interacting. They are attracting to each other. Why? Because of their positive charge and negative charge. Does it make sense? Okay. So remember that intra is always be something inside. Polar covalent bonding is the example of the intramolecular force. I'm calling interaction between the two separated molecules too. This, as I can see that, this is also be a dipole, isn't it? So what you see there is you have an interaction between one dipole to another dipole. The name of this is now therefore known as dipole interaction. Sometimes describe the dipole force between the two dipoles then. And this is one of the examples of the intermolecular force.
So intermolecular force is only for like part if the thing is partially negative.
Not only that, like this shows that one example of the interaction. I mean, there could be many other things. They do not need to have the charges to get interacted. There could be some other things, like for example, what if we have oxygen to oxygen? Okay, or the hydrogen to hydrogen. Now, I know there are gaseous molecules, but they are not really interacting, but still, we see that some gathers of the oxygen, gathers of the hydrogens. So what that means is there is some interaction between those. Without having the partial charges there could be some interaction. There could be some bonded together, kind of not bonded, they could be get along together too. They're not completely separated. They can come close together. But compared to having the charges, like partial charges there, this would be much weaker. So this explains why. Hydrogen to hydrogen, and that they're having some kind of we call the dispersion force, which is another type of the intermolecular forces. Dispersion force to be partial. It's actually sometimes known as non-polar interaction. Or sometimes described as temporally. Interaction due to temporal charges. Temporal charges. So when we compare that, this is something that very interesting comes in along too. Now, I just described that as the interaction between oxygen to oxygen or the hydrogen to hydrogen is really weak. It's really weak. So what that means is if I just flick it, it can just goes along because there are weak interaction, weak bondings to each other here. So this explains you why that comes in the gaseous state. That comes in gaseous state because they don't have good interaction between one to another. Gas would have the really weak interactions. What about water? Water is the only one of the things that comes in the liquid state in the room temperature. Why? They have a good interaction between the molecules due to their partial charges. They're quite strong. Okay, in the room temperature, 25 degrees Celsius, like now. Can you see that intermolecular forces can determine their physical state as well too? Yes, it does. Having the weaker dispersion force, weaker like in the intermolecular force means that the interaction between molecules are much weak, so that the state would be more like the gaseous state. Okay, means that it doesn't really, okay, I just need to flick it to separate them so that it comes in the gaseous state easily. even though I flick this water, because they are kind of bonded, they're kind of attracted, they're attached strongly. This makes what? Stronger interaction, which means the dipole-dipole interaction is much greater than the dispersion force given over here. Does it make sense to all? Kind of makes sense. Okay, so these two are the famous example of the intermolecular forces. Now, out of many dipole-dipole forces, remember the dipole again. When the hydrogens are forming a bond with nitrogen, oxygen, and the fluorine, it has the greatest dipole, the greatest change in the positive and negative. Does it make sense? Okay, then when this has actually happened, what actually happened is it looked like this. We have hydrogen and fluorines given, okay, which is one is partially positively charged, partially negatively charged here like that. Because the partial negative charge is so great, it almost grabs the hydrogen on the other side and forming a bonding. They're not really bonded because they are separate molecules. They are not really covalent bonded, but you just see that these two are almost like a bonded. It's almost like a bonded. Yeah, bonded. Remember, the bonding is actually kind of attached. They're almost like attached, like one molecules. So we give a very special name for that. This is still be a dipole, very strongest. This would be strongest dipole. Because still be dipole to dipole. One dipole to the another dipole is kind of attracted. Okay, when we talk about dipole, we give that as a set. We can't just have the partial negative nor the partial positive individually. We need to have a partial positive to get the partial negative. It's kind of consequences. Like we have a negative, then we can follow it by the making the positive too. It'll be the dipole too. Yes, it'll be a dipole too. So this means this is the strongest dipole interaction. Okay, so as they are the strongest dipole, we give a very special name. This is almost like a bonded. The hydrogen is almost like a bonded. Name of this is therefore known as hydrogen bonding. Something that you should not, or hydrogen interaction, hydrogen attraction, you can just memorize that as too. This still be a what? Inter, not the intra. Yes, we use a very special term bonding because they're almost like a bonded, like a covalent bonding strip, because due to that really strong dipole-dipole interactions, but still it's interaction between two molecules, not what something happened inside. So in summary, we have 3 different types of the intermolecular forces. Don't worry about this one. Yeah, that's basically what we talked about last time. Page 228, please. We have 3 different in terms. We have 2. One is the polar and non-polar interactions. Polar interactions, non-polar, sometimes known as London dispersion. You can't forget about. So don't worry about the London. This is name a person who found that dispersion force. We sometimes just describe that as dispersion attractions. It's basically temporally or the induced dipoles. They're the weakest. Followed by the dipole. Okay. Now, it's a partially opposite charge ions too. So anything that having charges like a partial positive and negative, we call that dipoles. Interaction between 2 dipoles called dipole-dipole interactions. But out of the many of the dipoles, hydrogen bonding is the strongest when the hydrogen forming bonding with oxygen, nitrogen, or the fluorine atom. Only 3. When hydrogen forming bonding with the chlorine, we do not call that as hydrogen bonding. Okay, this is between this to this. These 2 are interacting to each other, but they are not the hydrogen bonding. Does it make sense? Okay, so quick question, quiz. I have an ammonia. Okay, I have another ammonia. Okay, first, tell me about its intramolecular force. What is intramolecular force exists between what in that situation?
Nitrogen.
What is intra? What do you mean by intra? What's inside?
Inside.
What is the intramolecular force of the ammonia? There's only one answer. Intramolecular force in ammonia is known as polar covalent bonding. Do not confuse about the forces, get tricked by the forces. I'm simply asking you what type of bondings they have for the intramolecular forces. Okay? Then, what about intermolecular? What about intermolecular force?
Hydrogen.
It'll be called as hydrogen bonding. Which is what? Known as the strongest dipole-dipole interactions. Does it make sense? Okay, let's do one more. A few, actually. I have a methane to another methane. Okay, what would be the intra and intermolecular forces for these?
Polar.
Would it be polar or non-polar? Carbon and hydrogens. Carbon and hydrogen. I gave the example. They are the one having the very similar electronegativity. So it would be non-polar covalent bonding. What about their interaction between these two? Do they have any polarities? No, which means it cannot be the dipole-dipole nor the hydrogen bonding. Only things you can remain is dispersion force. Do not get confused about inter. You will. The reason why I'm emphasizing this, you will get this in module 7 next year in your year 12. You get lots of those questions asking you why we have such a high boiling and melting point of those. Let's do one more. Carbon with chlorine, tetrachloride. What about its intra and inter? Started from intra. What is the bonding between carbon and chloride called?
Polar.
Polar what? Polar what?
Covalent.
Covalent. Bonding. Very good. Again, they're still sharing the electrons. Okay. What about inter? If there's a polar, means this would be partially positive, partially negative, partially negative, partially positive. This would be then more likely dipole-dipole interactions. Does it make sense? Okay. What about this one? We have hydrogen to fluorine. Okay. And then we have tetrachloride. So these two are interacting now. So what would be this intra or intra? Polar what?
Polar covalent.
Good. Both of them are polar covalent. Both of those, okay? So positive and negative, negative and positive, good. What would be their intermolecular force then? It would be dipole. Can it be the hydrogen bonding? Why not?
Because the CCl4 is not.
It's not the hydrogen. It's not related with the hydrogen. Very good. So this is called the dipole-dipole. Very good. Shall we do one more? Okay. What about we have water with the nitrogen, with ammonia? So what would be the intramolecular force? What's happening? What's inside? What's inside water and this? Polar covalent. Very good. Covalent bonding. Then what about their interactions? It'll be hydrogen bonding. Because you see, this hydrogen will be attached, almost like attached to the nitrogen. So I'm calling this is the hydrogen bonding, not these bonding are hydrogen bondings. These are the polar covalent bondings. Okay, remember that, differentiate that inter to the intra. Inter is always be something happen between the molecules. Does it make sense? Yes, so this is what you need to understand about intra and intermolecular forces. Only three things you need to remember. Only three. Dispersion, dipole-dipole, hydrogen bonding. That's it. It's not that complicated, but I'm sure that you will confuse about intra certain stage. Okay, use that as your kind of guide back. Always think that as intra is talking about bondings. It's not about like interaction. It's about the bondings. Okay, depends on what type of bondings there, whether they're having polar or non-polar. It will decide to have what type of interaction they will have. Having polar covalent bonding is either be dipole-dipole or the hydrogen bonding, depends what they have. Having the non-polar covalent bondings would make the dispersion force only. Does it make sense? Okay. All right. Let's complete the page 129, please. I give you about 5 minutes to complete this one. Thank you. Okay, for those who's joining online, I will put it up your homeworks in the class 365 today. So make sure you download it, complete it. If you can send me the PDF forms, and I will probably able to give you marks back.
하이드로젠 본질이요.
음.
H가 N5S일 때만 하는 거예요.
Just giving you a guideline. Your homework is is this one. It's like a topic test question, so make sure you complete it. Get a hard copy. Now, when we're comparing the strength of the covalent bonds to the other inter, I want you to remember that it's much harder to break the bond between oxygen and hydrogen. What I mean is, if we have a water here, it's much easier to separate these two away than separating the oxygen-hydrogen bondings. So this is the reason why we tend to say intramolecular, inside molecular force is much greater, because it's hard to separate it. So let's talk about relative strength first of all. Covalent bonds are known to be strongest, stronger than, it'll be stronger than any other like stronger than any intermolecular forces. Dispersion force is known to be the weakest. Dipole is stronger than the dispersion force, and hydrogen bond known to be our strongest in the intermolecular only. So where do we find the dispersion force? It's, remember that dispersion force is talking about interaction. So it's in between. Which molecules in between the very good, non-polar molecules. I mean, there are dispersion force exists between the polars too, but compared to polar interaction, this is negligible, almost like a nothing. Okay, this dipole is in between. Yes, polar molecules. Lastly, hydrogen bonding is in between. When in between, yes, hydrogen to the nitrogen, oxygen, or the fluorine, and or yeah, H. Yes, no, not the H. It's in between. This one here, I'm talking about. This is the hydrogen bonding. Okay, that's what I'm saying. In between the two molecules that are joined of the hydrogen to oxygen, or hydrogen to nitrogen, or hydrogen to fluorine. The origin, covalent bonding is inside the molecules. So, in between. You can say like inside the molecules, the in between the two non-metals. Yeah, that's basically known as intramolecular force. Origins, where do we get those from? Dispersion force is basically partial or temporarily polar interaction. So what actually happened is in the dispersion force is they're rubbing, when you're rubbing something, okay, when you rub your hand, rub your things like non-polar, they're partially gain some charges due to the scratch. Okay, I'm rubbing something like really hard, then they partially attract to that. Just like you can think about some small electricity kind of produce that too. Just some things very kind of similar, but that's only called a partial or maybe temporarily. It kind of disappears after milliseconds or nanoseconds. Dipole, however, is formed between origins from two dipoles. That one from that the whatever, like we have some partial charges. Hydrogen bonds is between its origins from hydrogen to the nitrogen, oxygen, fluorine. So due to that strongest, due to that, you can write that here. You can continue here. Due to the strongest dipole, lowercase, dipole formed or generated due to electronegativity differences too. Very good. Covalent bonds are formed by origin by sharing the valence electrons. Okay, in between two nonmetals, we can say that as well. In between, just finish that. In between two or more nonmetals. So out of four, these three are intermolecular force in between the molecules. This is intra. Okay, make sure you remember that inter means you can just think that back as an interaction between one to another, one molecule to another molecules. Whereas intra will always be that something goes inside of the molecules in this case. Does it make sense? So we did quite a lot today. Started revising from the bondings. We also went through some of the VSEPR theory. Okay, let's quickly revise the VSEPR theory before you go. Okay, basic forms 2, 3, 4 attached. Okay, there are 8 as well, but we don't really go through that in high school levels. 2 linear, 3 trigonal, planar, and 4 tetrahedral. Make sure you write it down many times to get familiarized with yourself. Okay, this is deciding that what attachment to the center atom. Okay, so it depends on that. We can have the band shape. If you have some lone pairs, okay, and just quickly revise and writing down that too. Lone pairs as a attachment, lone pair as an attachment to. So for example, goes like this: water molecules having 4 attachments to the center atom with the 2 lone pairs. Then we counted lone pairs as like some invisible part, giving the shape of the band. Okay, so this is the kind of techniques that we use again in chemistry Olympiad. But you need to draw that. You need to know how to draw the Lewis dot or Lewis structures correctly. We also discussed about the difference between inter and intramolecular forces. So for next week, I'm going to go through some of the questions from your homework that I'm giving you today. Your homework's now uploaded on your class 365 on the resources part. If you have any questions or if you have troubles to download that, please let me know. I'll just send you the homework straight to direct to your emails. Okay, any questions? Or if you don't, okay, that's it for today. I'll see you all next week. Same lessons will be continuing on. I'm having the exact same class on Saturday morning too. So if you're interested, can join in that online. You have nothing to lose. Please let me know. Okay, just join that. Okay, that's all, guys. See you all.